Yeah. Okay, so uh, yeah, I think so. uh, it's only been it's only like slightly more than 1 month, but I already forgotten how to use OBS already, and need to make sure I remember how to record. So looks like everything is working now. uh, so let's get started. Welcome to quantum mechanics. For those of you who are new here, new to my classes, my name is Lim Yan King. So I'm from the physics department, and we are here to do quantum mechanics. So quantum mechanics is PHY 202. It's a year 2 course, and for everyone, even for those who are taking courses with me, right, it is, you guys are now year 2. So the way we are going to do things is going to be slightly different from the physics courses that we did previously, because now, in a sense, that we are, you know, doing real physics already. So it's going to be a bit more hardcore and more mathematical and things like that. So but at the same time, it's going to be more fun, because, you know, when you guys were in year 1, the topics that you have been studying actually is more or less the same things that you learn in high school, just that the questions are more difficult. But now we are definitely learning into new territory already. Okay, so, and yeah, so I hope everyone is excited as I am, because even when we were in the previous classes, we have been like mentioning a few things here and there about quantum mechanics, right? And everyone here has learned linear algebra before, whether you're a MAT student or a physics student. And for physics student, you guys were learning a lot of things about linear algebra and things like that. And some of you mentioned feeling confused about vector spaces and operators and things like that. Well, now we will really make use of it, right? So now we will actually see how we do all these things. Okay, so this is our so this is going to be most of our course over here, is actually to as I said in the lecture notes, quantum mechanics is essentially elaborate application of linear algebra to physics. So that is, in that sense, hopefully is going to be very interesting. Yeah, so a few things to keep in mind before we get started is that the administrative stuff. So I think the first thing to talk about is we have a public holiday on week 7, and either we replace class or on a Tuesday or something. So which one do you prefer? I think you guys, your timetable is free on Tuesday afternoon. Or since we are online, right? I see a lot of other people, other courses are doing the same thing, is that just continue anyway during the public holiday. So I don't know which one you prefer. So let's see what you guys think. Tuesday? You don't have holiday, right? Yeah. It's a Deepawali. Anyone here celebrating Deepawali? I have no idea. Probably not, right? Tuesday 1 to 3, you have class. Actually, me too, 1 to 3. So, actually, I have class on Tuesday 1 to 3. So I'm thinking like 4 to 6 or something. Just continue. It's okay. Continue is okay. So I guess, yeah, continue anyway. Any objection? Continue. So no one say no? Okay, good. Then easy. No need to find timetable and things like that. Okay, so that is the first thing that is settled. Monday you got 2 class. Yeah, so my class and what's the other one? Theoretical. Your theoretical mechanics is Tuesday and Friday, right? If I'm not wrong. No problem. Okay. Oh yeah, put 2 QM on Monday. Oh, okay. uh, Actually, that's possible. Do you want to do that? Um, okay, it's week 7, so we can decide later. I don't think you guys want 4 hours of QM. Your brain will be very tired. Yeah. Because imagine like a few times in our previous class, when we were covering some complicated concept and then some of you say, wow, your brain explode already. Imagine doing this for 4 hours. So maybe morning 2 hours, afternoon 2 hours, I don't know. So yeah, so I think for at the moment we continue anyway, unless we change our mind before week 7, we can discuss later. So it's 7 weeks from now. Do it slowly. Okay, so continue anyway. And then the second thing, right? So this is the part where it's different from previous class. I don't know whether it's good news or bad news to you guys, but our CA is going to be what was it? 40% exam. So our CA is going to be 40% final exam. And then wait, let me open this. I also don't remember the exact. We have 40 exam and then midterm and things like that. So yeah, 30, 15, 15. Okay, so we have 30% midterm. So our midterm, usually we will plan it on week 8. So week 8 we will have our midterm, and then you have 15% of the assignment. So assignment will be the same as what you did in the previous courses. For those who are new, I will explain the assignment later. But this new thing is the tutorial presentation. So the another 50% is the tutorial presentation. Okay, so the reason of our difference is, yes, no more quizzes. So we are replacing quiz by tutorial presentation. So that means when we in the last time I did the tutorial questions with you. So this time you guys do the tutorial. I think the way we will arrange it is we have about 16 people in this class. So over the semester, one person at least present twice. So you can choose one question or one long question or 2 short questions from the tutorial, and then you guys will present the solution that you got. Okay, so no more quiz, and I believe this will be good news compared to last time. It's less stressful because we shall not. So the main part is to let students practice presentation, because most of you guys haven't really experienced presentation type of things yet. So this is one chance to practice, and you guys present the tutorial solution. We don't care whether it's correct or not, right? The main point is to let you guys practice the presentation. So just try to give your answer, and then it's really a tutorial style. So usually this is what we would do if we were in a physical class, but we have been online for too long already, so we cannot drag. So I think at least right now we should at least start trying to do it through online. Okay, so that is our so that is the new thing. So instead of replacing to quiz, assignment topic, yes. So assignment topic I have already uploaded already. So do quantum mechanics related questions. Yeah, but I'm supposed to explain later lah. So tutorial presentation, I think what we're going to do is I will do it in alternate weeks. So we can start on next Monday, the 2nd hour. I will let you guys volunteer and see how it works. If nobody volunteer, I will just randomly choose someone to present. So But the earlier you volunteer, the more questions you get to choose, right? So that is also an advantage for volunteering early. So you guys present your answer, and this is online, so you can decide whether you want to write. If you have tablet, you want to write it and then you share screen, or another way to do it is you can prepare slides or something like that. But it's just like 1 or 2 questions. Okay, so it then yeah, so this one is just for you guys to present. No stress about this. Whether your answer is correct or wrong, I will let you know like as you present lah. We can the whole class we can discuss together the answer. Okay, so that is the thing about quantum mechanics. It's not for beginner, is you need to get used to it, right? So it's not the same thing that we did last time. Okay, so that is our style for presentation. And then yes, so the second thing to talk about is the okay, so we start next week. We start next Monday. Yeah, is there anyone want to start already? Want to volunteer? Probably too early to tell, right? I haven't even tell you anything about quantum mechanics yet, so never mind. Okay, but the assignments. Okay, so let's talk about the assignments. PPT. Okay, yeah, PPT also can. Your Microsoft Word also can, or LaTeX or something. Assignments. So 15% of the coursework is coming from assignments. If you have taken the previous course with me before, you guys know exactly what this is. For those who are new to me, right, assignment is just to answer one of these 7 questions. Okay, so you choose one question. It is a topic for you to explore and read up, and you search online for information, and everything that you learn, you write it in a type of a report style. So your report, usually I will not fix the page or word length of the report. You just write down what you learned, and based on previous experience, most people, the report end up to be 5 or 6 pages. That is fine. Okay, and it's basically just to like address the issues that is covered here. So you do what you can, like study what you can about these topics, and try to just try to write out what you know. Okay, so the idea is this also, like the following, is just to let you guys have fun and enjoy like strange and exciting new topics that is not covered in the lecture notes, because lecture syllabus is standard and dry and very boring. So at least I try to choose the question to give a chance to read up, like, and watch YouTube videos is also fine. Look up like something interesting topics and see how the knowledge of quantum mechanics can be applied into topics that is outside the syllabus, because syllabus stuff tend to be boring. So let's try to look up some exciting stuff, right? So the things that I can think about is a lot of advanced research, because with quantum mechanics is a current research topic, so a lot of things are going on right now. For example, quantum computation, and then microscopes. There are several types of microscopes. Quantum teleportation, we hear the word so fancy, right? In Star Trek you got teleportation, but what is real teleportation in real life? Quantum teleportation, that is a calculation. By the end of this course, you should be able to learn how to calculate an example of quantum teleportation already. So that's pretty cool, right? So that is one thing. And then the fourth question is about lasers. In chapter 2, we will talk about masers. So what are lasers and masers? Well, we shall find out in chapter 2, and once you learn that, maybe you can start to explore these kind of topics. And then particle physics, I put that in because I remember a few questions about particle physics already when we were doing EM. Some of you were interested in particle physics. And then cold fusion. So cold fusion is another quantum mechanical process, and this is actually Spider-Man's assignment. So I will talk about that later. Is something random, but otherwise you can propose your own problem here that is not covered under here. Just tell me any other topic you are interested in. You can you can do it. Okay, so Prof Ong style. Oh, Prof Ong style on, yeah, writing on the PPT, right? So that is also another thing. Okay, yeah, so that is the thing about assignments. Any question about assignment, especially new students? Hopefully it's clear. If not, you can ask me questions later. Then the last thing is also physics student knows already, but for the new students, usually every Wednesday there is a seminar on the main campus, and it's online. At 12 p.m. Okay, so every week there is some research topic that someone will present a research, give a research talk, so you can sort of see what is also happening in current research and things like that, right? So yeah, this semester I will give one also from here, and my talk should be on week 3, I think. So I will talk about my research on this week 3 on Wednesday. So it's 12 p.m. to 1 p.m. It's called the Wednesday lunchtime seminar. Okay, so yeah, I guess that's about it for the administrative stuff. Does anyone have any question? If not, we shall get to our we shall get to quantum mechanics. Yes, so I'm gonna talk about a result that we got recently. I was working with a colleague from math department, and we submitted a paper that is hopefully going to be published soon. So I will present that result. Yeah. So that is the research seminar things. Okay, so yeah, we are going to quantum mechanics now. What is my screen showing? Okay. Hang on. Okay, so yeah, I think we can start talking about I think it's pretty cool too. Yeah, I'm quite excited to talk about it on week 3 because the result is a bit unexpected. So let's begin with quantum mechanics. Okay, so it's still the first lecture, so I think it's still a bit easy and breezy for now, but let us talk about this for the moment. All right, so let me introduce to you what are the main concepts that we will be addressing. Hang on. Yeah, it's after holiday. I'm not used to using this system already, but I think everything is working fine for now. I'm still recording, right? Yep. Okay, so let's go to quantum mechanics. Right, so just a bit of an introduction, a bit of a comment. So in my lecture notes, right, I have kind of like written a very almost like an essay about this kind of thing. So I'm gonna discuss a few of those points here, and I mainly want to discuss so that you guys don't feel too scared. The main reason is because outside of physics, right, every time you hear quantum mechanics, it always seems like a very difficult topic or very strange and things like that. So, and you guys might feel scared, right? So if you're taking this course on quantum mechanics, is it going to be a difficult course? I would say no or yes. It's just another course. We have done many courses in physics before, right? EM, mechanics. You guys are doing theoretical mechanics now. This is quantum mechanics. So difficulty-wise, I would say is the same. Whether you find physics difficult or not, you have already seen all the other physics course, right? It's just another physics course. The reason why it has a reputation of being difficult is because the concept and the philosophy underneath quantum mechanics haven't been fully understood yet. So I don't know how much you've heard of it before. We will discuss this a bit later. Is the philosophical thing is like whether an object can exist here or there or at multiple places at the same time. Quantum mechanics seems to imply that the object's existence is questionable. So that is very strange. And yes, this question is hard to answer. In fact, as of now, nobody can answer this yet. That is the reason why quantum mechanics is difficult. But our course is not difficult because we are not handling this question. Okay, so we are doing it the same way as any other physics. We will learn the main laws of quantum mechanics, and we will learn how to use the law to solve problem. In other courses, you have done this for Newtonian mechanics, learn the laws, solve problem. Previously, you've done electromagnetism with me. You learn the Maxwell equation, Coulomb's law, solve problem. In this course, we will learn Schrodinger equation, solve problem. So in that sense, it is not difficult. Okay, so it's just another physics course. And if you want to say, okay, there's a slight increase in level because what we are going to use now is a bit more mathematics. And bit more mathematics just means that we are applying linear algebra. The concept that you learn in your linear algebra course, we will apply it quite often here, which we haven't done that yet in year 1 physics courses. So, but the math student and physics student, everyone already learned linear algebra. So now we will apply the things that you learn into here. So in that sense, I hope it's going to be very exciting, right? Because you have spent all the effort learning linear algebra. It's very abstract. Don't really understand like what is the significance. And here it is becoming very significant. And it will sort of touch a little bit here and there about the philosophical questions about whether an object can be in multiple places at the same time or not. So I will refine this question a bit more later. And there's a lot of misconception in quantum mechanics. So we are going to talk about this pretty soon. Okay. Yeah. So as you guys know, right, time goes really fast during the semester. And it somehow is like that. Okay, so this is my initial speech just to encourage you guys to don't need to feel scared about this topic. Okay, it's just that if you see in movies and things like that, the reason why we feel quantum mechanics is difficult is because in movies they say, oh, quantum mechanics is usually the characters say quantum is just to convey something that is very complicated, but that's all. But most of the time that's not true. Okay, in fact, right, in the first Transformers movie, there is a line that I think everyone will forever remember because we're gonna do this here also. There's one character who say, right, in the first Transformer movie, there's some computer hacker trying to hack the robot system, something like that. I don't remember, but I remember one character say that it's too difficult already. What they say is we should stop using Fourier transform and use quantum mechanics instead. So what the character is trying to say is that try to use more advanced method to hack the robot, right? So don't use Fourier transform, use quantum mechanics. But what we will learn in this course is nonsense. Fourier transform is actually everywhere in quantum mechanics. So in fact, Fourier transform is related to the uncertainty principle. Okay, so actually what you hear outside about how difficult quantum mechanics is, most of the time is going to be nonsense. It's going to be the same thing here. So that is another thing I'm trying to encourage you guys to don't feel scared. Okay, so now before we start, let us recap a few things that you might have learned either in modern physics or in high school if you haven't taken the modern physics course. Is that what the basic idea that we learned here is that previously, right, whether in high school or in modern PHY 104, is that we have already covered some of the early ideas of quantization. Okay, one of the objects that you have learned that is quantized is photons. So photons is the quantization of light. Okay, so this is light, right? So what does photon mean? It is to say that light, in other places you have learned that light is electromagnetic waves, but in when we quantize the theory of light, it becomes photons. And what it means is that light consists of discrete packets of energy, and the energy of the photon is given by the Planck constant times the frequency. Okay, so do you guys remember this? For the math student, if you're confused here, just ask me, right? I'm just trying to if not, I'm just explaining here as a review. Okay, so you have learned that light is a packet of energy h times f, right? Where h is the we call it the original Planck constant. So Planck constant. Okay, so the original Planck constant is h, and the value is 6.63 times 10 to the minus 34 joules per second. And this is a very small number. So the reason why we did not notice quantization for most of our history until recently is because it's a small number. So you only need like very precise technology to be able to detect the discreteness. Otherwise, you can only detect huge chunks of energy, so it doesn't appear quantized at large scale. But if you look at atomic scales and things like that, then it's quantized. So quantum mechanics is important for atomic scales. But in this course, right, this is an important number, but we don't actually use this number. We use another number that is divided by 2 pi. So in this course, we often use this one instead. It's pronounced h bar. People call it h bar, and because we do h with a bar across it, so it's just h divided by 2 pi, right? So numerically, the value, I believe, is let me check, 1.054572 times 10 to the minus 34. It's just this number divided by 2 pi. So it's joules per second. That is the unit for h bar. In atomic experiments, right, most often people use the electron volts units. So in electron volts, 6.5822 times 10 to the minus 16 electron volts. Okay. Now, also again, right, unlike year 1 courses, we will seldom use calculator now. Okay, and most of the time it's like pure calculation. So we will be more used to doing this, because when you use Schrodinger equation and solving a lot of problems, we will realize that actually h bar is more convenient. Otherwise, if you use h, you need to write 2 pi everywhere, so it's going to be messy. So instead of 2 pi everywhere, you just write h bar. So in terms of h bar, right, h bar, the photon energy, so we should rewrite this using h bar instead of h. So the photon energy is what? So h is 2 pi h bar, so E is equals to hf. So h bar is just bring the 2 pi over, so it becomes h bar 2 pi and then f, and the 2 pi appear here, but actually 2 pi f is just the angular frequency, right? So we call this omega, and this is also the expression that we will use quite often, is h bar omega. This is the angular frequency. Okay, in fact, if you have been solving wave equation previously, we use omega more often than f, right? Because it's kind of the same reason, like 2 pi appear everywhere, so just call this whole thing as omega and this. So usually this is the basic quantum of energy. Okay, so this is what you have learned last time. If you haven't learned this before, this is just a very quick recap. That is the important concept that we will use here quite often. Okay, so that is about photons. Yes, time is relative, so that's why. Dirac C, okay, Dirac C is about antiparticles. So actually, to understand Dirac C is more beyond quantum mechanics. It's like quantum mechanics 2 or 3, unique quantum field theory. But I will mention this a bit later when we get a chance. Okay, so the idea is that just a preview, because quantum the Dirac sea is like we imagine our vacuum to be a quantum state, right? So if we vacuum to be a quantum state, and then if I create a particle out of nothing, right? So you get a particle out, then by conservation of energy, there is an absence of particle here, and that creates the antiparticle. So the Dirac sea is related to the particle and antiparticle. It is one interpretation, but the interpretation that we'll use here is by using the uncertainty principle plus conservation of energy, right? So using pure energy, you can split into a particle and an antiparticle. An antiparticle is interpreted as a gap in the Dirac sea. So that is one thing. No more calculators. Not to say zero calculators. Sometimes you might calculate some values, especially when we go to hydrogen atoms and things like that. But yeah. So it depends on whether it's more difficult or more. Calculator is more prone to mistake, right? Because you press the numbers and stuff. Okay, so another thing about another basic concept that is earlier known before the birth of Schrödinger equation is the idea of the wave-particle duality, right? So just now we have said that, okay, in electromagnetism course we learn light as a wave, but in quantum mechanics we learn light as a particle. So is it a wave or a particle? Because wave is looking like this and particle looks like this. So these are like very different concepts. This is what the philosophical part, like how can something be this and this at the same time? So that is the philosophical part that I mentioned earlier, right? No one can really understand at the fundamental level, but what we do know and what we use for now is the de Broglie formula. Okay, so this is de Broglie is a French physicist, and so the French pronunciation is de Broglie, right? So I know a lot of people will call it de Broglie, but what is the de Broglie formula? So the de Broglie formula is to relate, okay, whether it's this or this, there is a formula to relate the two quantities. So if I take the particle description, right? So if I have a particle of moment, so I can relate the momentum of the particle to the wavelength, because if I have a wave description, right, the wave description is going to have a wavelength, but the particle will have a momentum. So the wavelength is something to describe a wave, the momentum is something to describe a particle, and according to the de Broglie formula, the particle of momentum p is related to a wave of wavelength lambda, right? So the de Broglie formula is just very simple, h divided by lambda, okay? But again, as I said, right, we will seldom use h, we will use h bar. So h is 2 pi h bar, so we got 2 pi h bar lambda, and you see 2 pi lambda is something that might be familiar. We call this k, right? So we relate this as h bar k, right, where k is 2 pi over lambda. Does anyone remember this? This is something we call the wave number. Okay, so that, yeah, basically that is about it, right? What is k? Is nothing special, it's just 2 pi divided by the wavelength, and we just give it a name, wave number k. Okay, so the momentum is just h bar times k. So this is the de Broglie formula. Okay, now momentum is a vector, so actually we can generalize this in terms of a vector. So k is the magnitude is 2 pi over lambda, and then the direction will tell you the direction that the wave is traveling. So that is the wave description. Okay, so another early concept about quantum mechanics is the idea of the wave function, right? So wave function. In fact, we will spend a lot of time doing wave function later, so I'll just briefly mention. Okay, so the difference is because in classical mechanics, right, the position of a particle is fixed. Okay, so let's say an x coordinate, not to say fixed, but it's precise. Okay, if you use Newton's law, you can calculate exactly what is the position of the particle at exactly what time. It is precise. But the problem now in quantum mechanics cannot be precise. So the position can only describe with probabilities. Be described with probabilities. Okay, so how do we get the probability? So the probability distribution function is the modular square of the wave function, right? So this is the wave function. Okay, so the wave function itself doesn't have a meaning. In fact, I remember someone asking me before, right, what does the wave function mean? Okay, wave function doesn't mean anything, only the square is the probability. So you can say that the wave function is the square root of the probability. That's the best we can do, right? But why is it like wave function? Why we calculate the wave function instead of the square root is also kind of a very strange structure of quantum mechanics. Is because the interference happened at this level, right? So the two if the particle behaves like a wave, then the probability distribution, you calculate psi first, right? You find this function, and then you square this to get the probability distribution. So once you get the probability distribution, right, the probability, now you can use this to get our answer. So let's say I want to find the probability of finding the particle between A and B. You do it like the probability way. So you integrate from A to B of your probability distribution square. So normally probability is going to be some distribution, right? And then what is the probability of the finding the particle between here and here? You find the area under this curve. Okay, so this is the plot of psi square against x. So this is the probability distribution. Okay, and then yeah, so the particle's position is probabilistic. Okay, so you remember all this, right? So some of you have used this before, right, in modern physics. Yes, yeah, so P is h lambda. Oh yeah, this one was earlier, right? The direction of the wave is traveling. Yes, exactly. So what you say here is correct. Yeah. Okay. So what's the next thing to that you have been learning? So what you have been learning previously, it was about the uncertainty principle, right? So the uncertainty principle says that the uncertainty in x times the uncertainty in p is greater or equals to h bar over 2. Okay, so the product between those two must be greater than a non-zero number. H bar is a small number, right? It's a small number, but it's not zero. So if you want to be certain in x, it becomes uncertain in p. And similarly, if you want to be certain in momentum, it becomes uncertain in x. Okay, so what does uncertainty mean here exactly if you are using the language of probability distribution? So let me show you an example. Right, so usually the graph that we often deal with quite often is like the Gaussian distribution, right? So the Gaussian distribution, the part at the center is going to be the mean, or we call it the average, or the expectation value, right? So if this is my x value, then this is my expectation value in x, and then the uncertainty is how wide this is, right? So this is the uncertainty in x. So if you're learning statistics, right, it's going to be something like it's going to be related to the square root of the variance, something like that. Okay, so it is about the uncertainty because we're talking about probability distribution. So all these values are possible, but this one is the most possible one. These are least likely, but the most possible one, what is the plus and minus range? okay? Because we will not definitely get exactly this value all the time, but you know, sometimes more, sometimes less. So how sure can you be? If this is a narrow spike, that means we are very confident we will get this value. That's certain in X. But uncertainty principle, if I get a narrow spike in X, I become unsure in P already, and vice versa. So this is one of the issues that we need to deal with quantum mechanics. Okay? Okay, so that is the uncertainty principle. Now, the next thing is another central concept about quantum mechanics is the superposition. Okay, so superposition, you have encountered this in other areas in physics before. For example, in electromagnetism, right? You can take an electric field that is one electric field plus another electric field. All you get is a new electric field. So the same thing happens here for quantum states. So that is different for particles, right? Particles, in Newtonian mechanics, you calculate the momentum. The momentum is one value at one time. But in quantum mechanics, if I describe a particle with a wave function, okay, if I take one wave function, it will describe one distribution, one state. But if I take another wave function, I will get another wave function. Right, so we call this state 1 plus state 2, then I'll just produce a new state. So this is where the weird stuff of quantum mechanics starts to happen, because for example, right, this is the famous cat experiment. Okay, so for example, let's say this state describes a particle of spin up. Right, so particle spin up means the angular momentum is rotating this way, and then this is spin down. Right, the angular momentum is rotating the other way. Okay, so a particle can have spin up or spin down, but in quantum mechanics, they can exist at a superposition state. So this is where the strange thing happened, and this, how to say? This is where the strange thing happened, and I think the way to say is just to talk about the cat experiment, right? So have you heard about the Schrodinger's cat before? I'm sure some of you heard of it before, right, at some times, right? So the idea is this, okay? So I have, I put a cat in a box, right, and yeah, let me draw a cat. Right, so a cat in a box, okay, and then I have a particle source. It is a source of particle that is in state 1 plus state 2. Okay, so this particle, I don't know whether it's pointing up or pointing down. Okay, but I have a detector. So this detector, right, contains poison gas. So for example, the detector will release poison if the particle is in state up, but the cat is safe if the particle is in state down. Okay, so this is the philosophically weird part. We will not deal with this quite often, but the question is this, right? We will learn in quantum mechanics that a wave function can exist in a superposition of state. So superposition of state means like kind of like both at the same time. If it's both at the same time and this experiment is happening inside the box, then is the cat alive or dead? Okay, so the philosophically weird thing is, how can an animal be alive and dead at the same time? Is it alive or is it dead? Right? It's one or the other. And the only way to find out is to open the box and see inside. So that is, but then, right, before you open the box, you don't know whether the cat is alive or dead. After you open it, there is a chance to see it dead, there's a chance to see it alive. Never both at the same time, but you can also never be sure what you will get. And this is the difficult thing of quantum mechanics, because it's like the observation seems to determine the outcome. It's not very clear here yet. The next experiment I will explain and show how weird it is. Okay. So yeah, so superposition means the cat is alive and dead at the same time, but if you are the cat, what do you think the cat is experiencing? Right? Is it alive? Is it dead? Is it like choking from the poison, or is it just doing nothing? Right? So we are tempted to say both at the same time, but also cannot, right? Because imagine you are the cat, so the cat is doing something, but what is the cat actually doing, right? So that is one of the questions to address here. Okay, so well, if you hope you are the cat, I guess definitely not this cat, right? Because there's a poison there, so very dangerous to be a cat. Okay, so now I mentioned something about the observation affecting your outcome. So it will be more clear if we talk about the interference experiment. So waves or particles. Okay. So I've written a lot of details in my lecture notes already, but I will cover this very briefly here. Okay. So this one is something that we kind of already learned from our other courses of physics, like the wave interference, the double slit experiment. Okay, so if you use a double slit experiment, but if you shoot it with a gun, this is good that I'm John Wick, right? So I'm shooting bullets. Okay, but this is not like John Wick, because John Wick shooting is very accurate. This one is a bullet that is shooting in random directions. So actually it's not like John Wick at all. Shooting in random directions, and then there's a wall at the back. So what do you see? You will see bullet holes on the wall, right? So let's draw another view of the wall. So if I'm shooting a gun in random directions at a part with two gaps in it, then what we expect is most of the bullet will pass through this gap, most of the bullet will pass through another gap, but sometimes it will bounce, right? And it will end up somewhere else as well, but there will be less and less bullets over here. Okay, so if you can plot the density, bullet density, okay, is like, okay, the light coming from gap number 1 and gap number 2, the bullet, well, the probability if you use random is P1 here. And if you just ignore this, and if you just if you close this hole and you just shoot this part, you get another probability distribution here. So this is P2. Okay, so if you close one hole, you get this shape. If you close another hole, you get this bullet density. Okay, so if you open both at the same time, you just get the sum of both. So roughly speaking is something like this. Okay, so this is the red one is P1 plus P2. Okay, so this is what happens for particles. Particles, if you close one gap, you just get the independent one, the other one. You close the other gap, you get 2. So if you open both, you just get the sum of the independent probabilities. Okay, but what if you do this experiment using waves? So this is the electromagnetism, right? So we spend a lot of time doing this in electromagnetism, right? So we see what we observe on the screen, right? So what we observe on the screen here is the interference pattern, right? So remember what you observe. You observe the bright fringe and then the dark fringe, but bright and dark and bright and dark, right? So so this is what you observe for the intensity. Okay, But this is different if you close one hole. So if you close one hole, you do not get the interference pattern. You just get a single slit diffraction that is not so obvious, right? So if you close one hole, you just get like a spike here, and then another spike here. So this is I1, this is I2, right? So the reason is because, well, the interference is not, the I total is not equals to I1 plus I2. We know this already, and the reason why this happens is because the interference is not happening at the I, it's happening at the electric field. Okay, so remember this. So let's say our electric field coming from slit 1 is the direction cos kx minus omega t. See, we use the omega here, right? But this is for light. So, and then E2 is E0 cos kx minus omega t, and we did this last time. We plus a phase difference, right? We plus a phase difference. So you calculate the E total is just E1 plus E2, right? So you calculate this is not our, we are not doing an EM course, but the main point is, if you get the total, the intensity is half epsilon C, the E total square, right? So you interfere already, you get the total, and then you get half C epsilon, and then the magnitude square, and then cos the phase difference over 2. So there is a cosine square graph, and this is why you get the cosine square. So the reason why I go through all this is because we understand what do we get if they are particles, and we understand what do we get when they are waves. Okay, so this is just to remind you, right? Just to also to establish this concept. The strange thing starts to happen when we do the experiment with electrons. Okay, so let's see what happens if we do it with electrons. This is page 3, is it? Okay, so in ideal conditions, and we use electrons, so ideal condition means no external forces, in vacuum, the best vacuum that we can do it. If you emit a bunch of electrons here, right, and then pass through 2 holes, and then you collect the electrons on the screen. So electrons are particles, so we expect them to behave like bullets. So what do we see on the screen? Okay, so on the screen, it turns out, right, we can actually do this experiment. So if you just shoot 1 electron, when you collect on the screen, you get 1 electron detected here, all right? Then if you the second electron pass through, don't know what happened to it, but you get another here, okay? And then you get more and more electrons. Okay, maybe some are here, and then some are here. So this is the difference, right? It's not to say that the individual electron is both at every place at every time like the cat, but it follows a probability distribution. If you do this experiment long enough, right, okay, another electron will come here, another will come maybe here randomly, maybe here, but if you do it long enough, you realize that they all accumulate in the interference fringes. So that is the strange thing, right? They are particles, right? You can hit the wall and you get a bullet hole just like the bullets, but the pattern actually following the wave. So that is the wave particle duality, right? It's bullets but also wave at the same time. So if you plot the graph of the electron per meter, electron density per meter, you do get this cosine square pattern. Okay. So people have actually done this experiment. I will show you the lecture notes, right? So people have actually done this experiment, and this is like what I said. So this one, they actually record, like each point is the position of an electron hitting the screen, right? So many points here, the electron hit the screen. So they keep on doing it. After a long time, they start to observe this pattern. rather than the John Wick shooting randomly at the screen kind of pattern. Okay, so that is the strange thing, right? So that is the thing about the electrons. So okay, before we go to the break, let me make the situation more complicated. So okay, when you do this experiment, right, you get this strange result. Okay, so what is it that about the motion of the, if you're still believing that electrons are particle, because what you detect are particles, so what is it about electron that how do they move such that they get this pattern? So you want to investigate, right? Especially if you're an experimentalist. So if you have to investigate, what you want to do is you want to track the motion of the electrons. So you prepare the same set of electrons, right? You shoot the electrons, and then you just, this time, you follow how they go on the screen. So you observe, right? So you observe. This is your eye. This is the detector. This is where the strange thing comes in. Okay, so let me make the screen more narrow. So if you try to follow the individual electrons, if you look at the electron and see how it goes, because we want to find out how does the group of electron scatter until they get this shape, right? So let's find out. Let's look at them. Let's see how they move. But if you see how they move, right, if you follow the electron, how they move here, and then maybe another electron moves somewhere like this, you actually change the experimental outcome. Then you get the bullet result. So what you get is this. So this is the strange thing, right? So observing the electron changes the result. That is the huge headache that people are trying to encounter this for the quantum mechanics. So that as I said, this is the philosophy. Like observing something sort of influence the situation, because we are not used to it, right? Because people say, okay, we are neutral observer. You look at it, you don't disturb, right? You just look at it from afar. But just looking at the electron will change your result. Okay, so that is the weird thing about quantum mechanics. And yeah, so I think for now I should probably let you guys take a bit excited to learn about the strange symbol, because when I took quantum mechanics as a student, I have a friend who loves quantum mechanics. You know, he saw all this thing, and then he said that the symbol looks very cool, especially if you write it out on a whiteboard. It looks like very impressive, more than your normal equation kind of things. Wait, hang on, am I recording? Testing. Is the, hang on, let me just double check the recording that is here. Okay, I think it's good. I forget. I already forget how to use the system. Okay, so now this is the strange thing, right? But let's say at this point of history, people have done this study, have done this experiment. What at this level of, what are the conclusions that we can draw based on all this outcome? So one thing is that the observation affects the result. So this is one of a huge consequence of quantum mechanics. Observing the particle influences the outcome, experimental outcome. Okay, so this is one of the huge thing. And then now, if we detect, right, we study the motion, it becomes this. If we don't study the motion, it becomes this. So what kind of motion that produces this is the only way we can to make sense of these two situations at the same time is that a trajectory only exists when an observation is made. So if we do not observe it, then it's like a wave. It's like not one point moving on a curve. So trajectory, right, by that I mean like the motion of the particle, it follow a curve at some time t. Okay, so it only exists when you observe it. So if you don't observe it, it's like superposition, like the cat is dead or alive. It's slit 1, slit 2, don't know. Okay, so that is one consequence of this. And then before observation, we got the wave behavior, right? So wave behavior, instead of this trajectory, we got the wave behavior. And if you recall, wave behavior is given by the wave equation. And now we know that we will call this our wave function. Okay, so wave function square is a probability, but the wave function itself, we will give it a name just to be convenient to refer to something. We call it a probability amplitude. Okay, and then so in order to understand this, the probability is after you interfere the waves, right? The same thing for intensity is half C epsilon E1 plus E2, right? So that's why there's a distinction between the wave itself and the square. So if you're talking about electromagnetism, the electric field, they interfere, and then you square the result, you get the intensity distribution, the pattern like this. So same thing happens for the waves. Okay, so that is our situation that we have at the moment for quantum mechanics. So this is page 4. Next is page 5. I really need to get a haircut. The hair is quite annoying me right now. So yeah, it's always good to study hard, right? Okay, Cherry asks, if we don't open the box, the cat is like a wave. Yes, correct. The cat is always, yes. That is we are forced to draw this conclusion based on our experiments. In general means observation through equipment. Yeah, so in general, when I say observation, it's like some equipment or experimental. So eye is one way of observing, but if it's too small, you can't see it through the naked eye, so you need some kind of observation. And our eye is also kind of observation. It's like detecting photons reflected from things. Everything is it is considered as observation as well. Okay, so all these are the conceptual issues, and right now, before the next thing to do is, well, we need to develop some mathematics in order to formulate an equation or a law. Eventually, we'll go to Schrödinger equation, but in quantum mechanics, we will often use complex numbers. Are you guys familiar with complex numbers? Because if you're familiar, then we don't need to waste time talking about this that is boring to everyone, right? But for those who are not, okay, we will be using complex numbers a lot in this course. Complex number is just a number I that is defined to be a square root of -1. Remember? I think it's learned in high school, right? So it is a number that is, when you square it, you get -1, because normal numbers, if you square, must always be positive. But complex number is, if you square, you get -1. And a trick that we will use quite often is, what is 1 over I? So 1 over I, well, you can do this, divide top and bottom by I, and it becomes I divided by I square. So I square is -1, so you get -1. So the negative I. So the identity that I will use quite often is 1 over I, you just replace it with -I. Okay, so these are the complex numbers. Test, yeah. Okay. Okay, so in mathematics, right, we denote the set of numbers by some special symbols. So the set of complex numbers are denoted by C. Okay, right. Real numbers is our normal numbers, we denote by R. So in general, a complex number can be having a real part plus the imaginary part, right? So x plus iy. So this I is the square root of -1. And because I got the x part and the y part, I can actually plot this on the diagram. So we call this the Argand diagram, right? And let's take a random example. Let's say this is my complex number is here, right? So let's say this is 5 units from the origin, this is 3 units. So this is a complex number which is 5 plus 3i. Okay, so these are the complex numbers. And then, well, another operation that we will learn is about the complex conjugate. Complex conjugate, we change I to -i, right? So for example, z is equal to x plus iy. Complex conjugate is, I call this z bar, and I just change the I to minus. Okay, but it's z bar. But if you see the textbooks, actually in physics, a lot of physicists, they use z star, but sometimes z bar, and almost all mathematicians use z bar, and for us we will use z bar quite often. Okay, z bar is more convenient because star, for me, I feel like star wastes more time to write it down. Okay, so this is the complex conjugate, and every complex number, you can calculate the absolute value or its magnitude, right? So given a complex number z, the absolute value z is just x squared plus y squared. It's like finding the length of the vector. And also the argument, we call it argument z, is just the inverse tangent y over x, and we call this the theta. So because this is absolute value, it's the same as finding the length of this line from here to here. So we call this r, and then the argument is the inverse tangent y over x. So it looks like this angle theta over here, so we call this theta. And this argument in physics, in quantum mechanics, we call it the phase. Phase will be important in quantum mechanics. This will be the absolute value. Okay, so we notice that there's 2 ways to write down a complex number, right? So a complex number, you can give it a y component, x and y component, or you can express, this is like a polar coordinates. So this is r cos theta, this is r sine theta. So the a complex number can be expressed either using xy or I theta. And the way to link these two that is quite important to us also is the Euler identity, which is e to the I theta is given by cos theta plus I sine theta. Okay, so from here we can now relate the two, right? So to relate the two, we see that we notice that x is r cos theta, y is r sine theta. So if I take a complex number which is given by x plus iy, I can write as r cos theta plus y is r sine theta. So we notice that I can factorize the r outside. I got cos theta plus I sine theta. And what is this? This is e to the I theta. So e to the I theta, so we can write down as e to the I theta. So we call this the polar form of a complex number. Okay, so as you can see, this is the modulus, and this is the argument. Okay, so notice that you see, right? Actually, what is another way to write this? So another way to write this is, well, the modulus z, we observe that this is actually z bar times z square root, because z bar times z square root is x minus iy, x plus iy. So if you work it out, you get x squared plus y squared. Okay, and then you can actually calculate this again here. Let's see what happens. Z bar times z. So z bar times z is just r e minus I theta times r e I theta. So e negative power to positive power, they cancel each other, you get r squared. So the r is equals to z bar times z. So see, everything is consistent with each other, right? So that is our this is a very crash course in complex numbers, but it should be just enough for what we will be needing for later. So does anyone have questions about complex numbers? Everyone okay, right? Familiar, you have seen before. So for the physics students, you will learn more about complex number in mathematical methods 1. So I think next year or something. Is it next semester or next year? Probably next semester, April. For the math students, you have a whole course for complex analysis. That is in year 3 also, I think, if I'm not mistaken. Okay. Now, so I hope everyone is still following with me so far. Now let's go to a review. This is kind of a review of what we did, of what you guys did in linear algebra. But I will review this to explain the strange symbols that you mentioned seeing on the lecture notes. Okay. Vector spaces, right? So this is the thing that you learn in linear algebra, and we need to learn this. The reason is because quantum mechanics takes place in a special vector space which we call Hilbert space. Okay, so this is a certain vector. It is a vector space that uses complex numbers. Okay, so this is the main reason why I review complex numbers just now. You already learned. Oh, you already learned complex analysis. Oh, good. Okay, then I'm sure you learned about like the Cauchy-Riemann equations, things like that, right? Like I those topics are very interesting to me, and it's very relevant to physics also. But we won't be doing it here. We just use the basic concept like argument and things like that. Okay, so what is Hilbert space? Just to contrast, in classical mechanics, we learn Newton, right? So Newton's laws, Newton mechanics also takes place in a vector space. But the vector space is just R3. So this is a vector space with real numbers. Right, so when we write a vector in R3, we write x coordinate I, y coordinate j, z coordinate k, right? So that was what we did when we were learning Newton's law. But in general, vector space is more than just this. It can be many other things, including Hilbert space. So let us review the basic concepts of vector spaces. Okay, so what's a vector space? A vector space in general, right, to encapsulate this as special cases, a vector space is just a set. So let's call this set V with certain operations. Among its members. Okay, so what is the so in order for something to qualify as a vector space, you need to be able to do certain operations. So the first one is, I think it's very common and familiar with everyone. if you take a vector, you can multiply it by a number, right? So you need to have a scalar multiplication. Okay, so in particular, you have just a number. It can be a real number or a complex number, but if you times a vector, you get another vector. Okay, so if I take a number c times a vector u, I will get a new vector v. Okay, so this is basically like a simple vector multiplication. In R2 is very familiar, right? So if I draw an example in R2, let's say I take a vector v vector, and then if I 2 times this vector, I get a vector that is twice the length, 2v. I should call this u, and this is my new vector v, right? So this one is familiar, so it's scalar multiplication. Okay, and another operation to qualify as a vector space is I need to have vector addition. Okay, so basically I take one vector and plus another vector, I get a new vector. So again, an example in R2. Okay, so if I take a vector u and then plus another vector v, I get the new vector, which is right u plus v. So adding two vectors creates a new vector in a new direction, maybe, and a new length. Okay, so this is the vector addition. And then another thing that is important is the inner product. So inner product, in R2 we call it the dot product last time, right? I'll talk about duals later, but if I have one vector, I can multiply another vector to get a number rather than a vector. So there's a way to multiply two vectors to get a number. So let's say I take one vector u, I can multiply with another vector v. Okay, this is the notation that we use when we do Newtonian mechanics, but it will be more convenient in our course to use this type of symbol. So I take this vector and this vector, multiply, I will get a number. Okay, so I will explain the quantum mechanics one later. It's just that in quantum mechanics, you will just get a complex number or a real number, but the familiar case in R2 is, let's say I take 2i plus 3j, right? And then a v is I plus 4j. So you can calculate u dot v is just 2 plus 12 equals to 14. So you get a number, right? So it's just an operation over here. Same. Yeah, so basically the same. So the dot product is the same, but only when we are doing Newtonian mechanics, we use this symbol, right? But later when we do Hilbert space, we will use like those sharp brackets. And the reason why it's sharp brackets is because, well, let me explain. I think once you understand these brackets, right, it's going to be very fun to use. So how now, when we are doing R2, everything is very simple, but when you go to complex number, right, we really need to understand what's really happening in the dot product. When we take an inner product. Okay, so let's go to R3. Let's go to an example in R2. So R2 example again. Okay, so let's say I have a vector u, and now I should write this as a column vector. So let's say I got u1, u2, right? And then I take v. This is v1, v2. Okay, so we know in R2, I'm just starting with something familiar. It is defined to be u1, v1 plus u2, v2. So everyone knows this, right? But if I start from here, what is actually happening to get this? So this is actually, what we have here is u1 row vector u2 multiplied by v1 v2. So this will guarantee I can get it this, right? So what is happening here is, this is the transpose of this column vector multiplied by this vector column. Okay, so this is the transpose. Okay, so that means what is really happening, right? If I want to take two vectors to multiply this, to multiply u with v, right? We take the transpose of one of them, and then you do the multiplication. Okay, so we say that because transpose, every vector you can transpose to get a row vector. So in that sense, we say that we introduce the terminology U transpose is the dual of U. Okay, everyone understand so far? It's just to call this a special name, right? You can also say it's U transpose, but U transpose is for R2. So more generally, any U from any vector space has a dual. Okay, so that means the inner product means, right, so that means if I take a vector U and then a vector V, this is a dual of U. I should do it like this, multiplied by just V itself. Okay, so I need one of them, change it into a dual, and then multiply. So this might be the new concept for many of you guys, so I'll give a chance to ask questions. But is it clear? It's clear, right? Just if it's not clear, just remember this. So I'm asking because when I was a student long ago, when I learned this for the first time, I find it confusing. But if you guys don't find it confusing, then it's good. Correct, yes. We must transpose the left vector. Yeah. So the reason is because if we transpose the left vector, you get a number. But if you do this, you get a matrix. So yeah, the order must be important also. Yes. The dual, I should say for the math audience, it's not very precise language, but I think for the current purposes, just to avoid confusing ourselves, just, okay, if you're scared about the dual, just think this actually transpose, right? Because in general, there's actually more structure to the dual that is beyond just transpose. Transpose is only for R2, R3, Rn. But since we are doing these cases, so just imagine the transpose. Okay, so not in any case, but it is for the cases we consider now. Okay, so now we understand the inner product. Let's understand the next concept, which is called the orthogonality. Dual strong, what's that? Fancy, right? Yes. I think it sounds more fancy. Orthogonality also, in that sense, is a fancy term of perpendicular. So maybe when you're taking linear algebra, right, you have learned about orthogonal vectors before, and then you might ask, why use the fancy term orthogonal? It's just perpendicular. Well, it's a special case because orthogonal applies to things beyond directions, but in a special case of directions is perpendicular. So two vectors, let's say u and v, they are orthogonal if the inner product is 0. Okay, so if we take the R2 example, right, let's say I have one vector u is just pointing in the j direction, and then v is just pointing, let's say 5i, right? So in this example, u dot v is just u vector dot v vector is 0, right? Because they are perpendicular. Okay, so perpendicular is just means orthogonal in the case of R2, R3, and so on and so forth. Okay, but as I said, why we use a special name orthogonal is because later we will talk about Hilbert spaces. Hilbert spaces is a vector with complex numbers, so it's going to be more complicated than just this, right? So you can't even imagine what does he mean by something orthogonal with complex number vectors. But still, you can do something like this equals to 0. So that is why you have a special term here. Okay. Okay, so what else do we have? Well, another important concept is the norm of a vector. Another fancy term, but in R2 and R3 it just means length. It's just take a vector u, right? If I want to calculate the norm, I just take the vector, multiply by itself, inner product, and multiply by itself. Generally you get the square, so you take the square root, right? So if you take the example, R2 example, let's say my vector u is 3i plus 4j, right? What is the length of u? Is just 3 square plus 4 square square root, so the length of this vector is 5, right? So in R2 we call it the length, but again, when a vector is a complex number vector, what does it mean by length? Well, we call it a norm, right? It's something like the length. So once you got the length, right, given any length, we can always calculate the unit vector. It's just 1 over the norm. So this is a number, so you do a scalar multiplication times a vector, right? So if I want to find the unit vector of u, you just take 1 over the norm of u times the original vector u. Okay, so given this, right, let's calculate the norm of u. So if I take u dot inner product with u is just the original vector u divided by the norm, right? Original vector u divided by the norm. So it's 1 over norm square, and then u dot u. But this is also itself the norm square, so you get 1, right? So dividing by the norm will guarantee that you get it, you make sure it's 1. And this is a process that we call normalization. It is also something that we will often do a lot, many times in quantum mechanics. Okay? My hair is so long, it's very annoying. Okay, so what else is important when we talk about vector spaces? Vector spaces, usually you can define a basis. This basis is not unique, but at least you can find one is good enough. Basis vectors. So basis vectors are like your ijk unit vectors, and in a more general sense, I try to imagine this as the building blocks of vector space. Okay, And usually we want them to be orthonormal. That means when for a vector space V, right, there exists a set of unit vectors, okay, that are orthogonal to each other. So this is first condition, second condition. So this is first condition plus second condition. So if they are orthogonal and they are length 1, we call them orthonormal. But this such that any vector can be expressed as a linear combination of them. Okay, so the R2 example. So let's take R2 example again, right? So R2 is, we always have an x-axis and have a y-axis, but the unit vector, my orthonormal basis is one vector here and another vector here. They are perpendicular and length 1. So the basis, is not a unique basis, right? So a basis for R2 is, we have been calling this I and j, right? So any vector can be written as some vector u is some number I plus some number j. Okay, so any vector at all can be expressed as a combination of the vector I and j. Okay, so I remember last time you guys were confused about the concept of a dimension of a vector space, right? So we're going to talk about dimension again. So generally, this is, I have two bases. So this is a two-dimension vector space. So generally, if I got 3 bases, it's a 3-dimension space, or n bases, then I got n dimensions. So if there are n basis vectors, so if it's not ijk, right, if they're n, then you can't use not enough alphabet, so we just call this e1, e2, en. Then V is an n-dimensional vector space, right? So orthonormal means right, well, if I take E1 and E2, right, orthonormal means they are perpendicular to each other. So E1, E2 must be 0, and any number, right? So let's say E2, E3 is 0. Okay, but if I take E1 multiply by itself, E1 dot E1 is length 1, so it should be equals to 1. And then any number like E5 dot E5 also 1. Okay, so there's so many combinations. It's usually a shorthand to introduce this concept. To write this compactly, right? So let's say it could be E1, E2, E3, so I call this EI, right? I can be any number from 1 to n. And then I take another number, EJ. J can be some other number between 1 to n. So we notice that if the two numbers are different, I get 0. If the two numbers are the same, I get 1. So there's 2 possibilities. So this is 1. If I number equals to j, whatever this is, 1, 1, 2, 2, 3, 3, if they are together. But if there are 2 different numbers, it's 0. If I not equals to j. Okay, so we call this the Kronecker delta. So to define, to express this statement, we define, what time is it now? Okay, 5 more minutes. Okay, it's called a Kronecker delta. It's just a delta ij, so we call this ei, ej, and then we call this delta ij. Okay, what is delta ij? It's just a short form way to say this. equals, this is not equal, right? You can write this in matrix form as well. It's just the identity matrix. Right, so in matrix form is delta 1 1, delta 1 2, delta 1 3, right, delta 2 1, delta 2 2, delta 2 3, and so on and so forth. Then you just get the identity matrix. Right, and in fact, another more notation to introduce the identity matrix, I will use this special letter 1, identity matrix. Yeah, you can. Actually, I don't like to write it last time, but previously you always see me write the arrow on top is because we always use vectors in R3. Yeah, so for me, I write the arrow on top is to represent like the R3 vectors. So V usually is vector is R3. But in Hilbert space, yeah, I will introduce the Hilbert space later. Before we end, right, I should at least say one last thing about operators. So operator is something, is another fancy term. It might sound scary, but just to make it easy to imagine, right, it's just something that eats a vector and then it spits out another vector. Okay, spits out another vector. Actually, when I first tried to explain this, when I typing the lecture notes, I try to explain that something that eats a vector and shit out a new vector, but it sounds so bad, so I'll just say spit out. Okay, so let's say A is an operator. So the operator can operate on this, and then I get a new vector here. Right, another vector. Okay, so it sounds very fancy, but as you can see, right, it's just like a matrix multiplication, especially in R2. So in R2, right, a 2 by 2 matrix is an operator. Okay, so let's say I operate this on U1, U2. So an operator is A, B, C, D, and then operate this on, let's call this XY. Right, XY. So you get a new vector, right? So this is an operator. This is the vector. And you get a new vector. So you got AX plus BY. And then you got CX plus DY. So this is another vector. Okay. So one last yeah, just to finish off, one last thing that you have learned in linear algebra, right? What happens if I get if there is a vector that satisfies A times W, but is equals to a number times W, right? So the result is the length is unchanged, direction is unchanged. Just a scalar multiple of the original vector before the operation. So can you guess what this is? You have seen this in linear algebra, right? This is the eigenvalue. Yes, this is the eigenvalue. So we call this the so we say that W is an eigenvector of A, and then this number is lambda is an eigenvalue of A associated with the vector, because maybe you got some other vector that is also eigenvector, you get another scalar multiple, and this is you get out the eigenvalue. Okay, so you see, right, it's linear algebra coming in left and right here and there, but in quantum mechanics this concept is very important. The reason is because this eigenvalue will be related to things like energy, the energy of the system, or the angular momentum of the system, and things like that. So that is where the eigenvalue comes in. The energy of the hydrogen atom is actually the number, right? If you remember, it's like 13.14, 13 point something electron volts, 13.6 electron volts. The 13.6 is an eigenvalue of something. So that something is, this is the something that we will learn in this course. Like, how do we get it as an eigenvalue? Okay, so yeah, so I think we run out of time, so we can, there's a bit more things, but we can continue on this this Thursday class, and after that, on this Thursday class we will start to talk about the Hilbert space itself and the Schrodinger equation in quantum mechanics and all those kind of things. And then next Monday, hopefully some of you will start to present the first few tutorial questions. Okay, so yeah, so I think that's all for today. Any other question? 13.6 EV, right? Yeah, yeah, so let me stop the recording and I'll see you on Thursday.